So a warm welcome to this workshop, which we are having as the second event under the IDP ET talk series. Before we actually proceed to the workshop, I'll just say a little bit on behalf of the interdisciplinary program on educational technology about this series of talks, workshops or activities that we plan to have. The interdisciplinary program on educational technology is probably about 4 years, just getting very near to 4 years to date. And one of the things that would make it effective is our efforts to reach out to the community in which we are, the broader community in which we are. I mean the IITB, academia and the professors, students, and in fact even to the staff if required, if they find it useful. As far as making use of the research and the studies that we do in this interdisciplinary program is concerned. Obviously, educational technology is of importance to the institute because what we research here, what we study here, is supposed to make an impact on the way we carry out pedagogy. Being faculty from different departments, we are all faculty from different departments of the institute, we probably have our own conceptions, our own ways of delivering subject matter to an audience. But there have been systematic studies which indicate what makes that delivery or what makes a certain course more effective or less effective, what techniques can make it more powerful. And the aim in this set of talks, this series of talks, is to share some of the work that we are doing, and we hope that it will benefit the community at large. And of course, one of the things we hope is that as the talks proceed, you would have more and more participation from a diverse set of people in the institute. So without going too much further to describe what we aim to do in this talk, we will straight away go on to the talk today. I would request, of course, all of us know Professor Sahana Murthy. We are all familiar with her work, at least broadly. I would request her to say a little bit in the beginning about, the context of what she is going to describe, where it's important and why it is of importance not just to the researcher in IDP, but also to the IITB community at large. What kind of use it could be made of, what kind of use it could be put to in the pedagogy in the institute. And finally, of course, then proceed to your plan of the workshop. So thank you, and let's proceed to the work.
Okay, thank you, Professor Gadre, and good afternoon to all of you. So let me start by telling a little bit about what the series is about. Educational technology, the phrase, we would like to interpret that, and actually in fact even in literature it is interpreted a little broadly, in the sense at IIT we may be more familiar with technology as just the tool, but here we interpret technology both as the tool and as the other dictionary meaning, which is the application of a science of doing something. And the something here is the science of teaching and learning. So the formal definition of educational technology includes both technological tools as well as pedagogical strategies and other processes that are required for effective teaching and learning. And there is, of course, some emphasis on current technological tools like computers, internet, and so on. So what we have been doing here in the IDP is one activity, of course, is research into what are these different technologies and strategies which are effective for a given situation, developing these, doing large-scale evaluations and so on. But we've also been involved in a large amount of outreach activities, both the faculty and the students, because all of us, due to our profession as teachers, are at least consumers of this research. So even if we are not doing the research ourselves, there are some results which are very specific and useful and applicable to all of us in our daily professions. So this series of talks is actually aimed at disseminating some of that research and trying to customize it to your specific scenarios. That's why I wanted to focus on the midsem, because that's what's happening this week. So we'll see how that goes. Secondly, one more point which we've been focusing a lot in all our work in the IDP when it comes to pedagogical strategies is this concept of active learning and interactive engagement, which you may be familiar with if you've been following tomorrow's professor, this was from Tuesday, okay, this week. And this quote was actually by Richard Felder. And what he says is that active learning is engaging students, engaging not just in terms of attractiveness, but intellectually engaging them in the content, in course-related activities. The key things here, the key words here are other than watching and listening to the instructor. So what can they do other than watching and listening? They can be asked to read, talk to their neighbor, listen to their neighbor, draw, derive, interpret, brainstorm. There's lots of other things. So each of these where they go away from watch and listen and do something come under this broad bucket which is called active learning. And quick word on nomenclature here. So different communities in education research refer to this by slightly different names, and they are similar to each other. There's no need to go into the nuances of how they're different. It's just a tradition of a community, but we'll just take all these words to mean something very similar, and the definition was given in the previous slide. So sometimes even I might be mixing it up, and on different slides based on where it was sourced from, you might see either interactive engagement or interactive learning and so on. Again, the important thing here is that they're all learner-centric, which means the teacher is the facilitator who sets up the environment, writes the questions. Okay, requirements of active learning here. That the instructor creates very carefully designed activities, and students can do a host of things such as talk, write, read, reflect, express their thinking and so on. So talking to a neighbor is one possibility out of all of these. It is possible, but collaborative activities are recommended a lot because of their known benefits. Some sort of collaboration is highly recommended, and it's one of the last 2 points are important. So many of us do informal strategies where we ask questions, we get students to ask us questions, we respond to them. But when we say active learning or interactive engagement, they have to be derived from theories of learning, and they have to be evaluated repeatedly from empirical studies. Okay, so this is all of us really, and we do all of these are all good things. We pause and ask students if they understood. All good instructors do this. We even let students interrupt us. We also use novel technologies. We show videos, simulations, demos in class. So why is the previous slide, why is this really necessary, and why aren't these enough? So here I would just summarize 2 studies. Actually, one is a specific research study and the other is a meta study. And there are several others, but these 2 will give us an idea of why we need to go beyond these. We're not saying these are bad, but we're saying we need to go beyond all these points. So the first one actually is a controlled study, which the final outcome was that the quality of the lecture doesn't seem to matter in terms of students' learning. So what they did is there were 2 videos of the same instructor teaching the same content. One video was produced where the instructor spoke very fluently, didn't refer to notes often, didn't falter, made eye contact, good body language, explained things clearly in an engaging fashion. And in the other video, it's called the disfluent video, the instructor spoke haltingly, shifted here and there, forgot something, looked at her notes, and it was both on the same topic. And 2 groups of students, equivalent students, were made to view each of them. And then 2 things were done. They were given the same test. They both were given the same test on the same topic right after they watched the video. And they were asked a series of questions on did you think the instructor was engaging, did the instructor know her material, did you learn well, and so on. So first, before actually scoring their test, students were asked to give their own perceptions of how much they learned. It turned out that 2 important points came out here. The students in the fluent video said that their perceived learning was higher than the students in the disfluent video. But when they did actual measurements, the actual learning was identical. So then they calculated the overconfidence, the difference in the perceived learning and actual learning, and it was very high in the fluent video. It was about 20, when I say very high compared to the other, it was about 22% in the fluent video. So what the authors conclude is that the quality of the lectures don't really seem to be mattering. So the question we have to, quality in terms of these parameters, the fluency and the disfluency.
So how do we know that the lectures are of same complexity? Is it possible that the second lecture was...
The content was the same. No, the content was the same. But here it's it was the format and the delivery which was different, but the same activities were done, it was the same logic, same sequence and so on.
So the two groups of students?
Two groups of students who were measured to be equivalent.
So I was curious about...
In what sense? So they were all from the same class, for example. There was some, maybe their previous marks were seen for achievement. They also, when we look at equivalence, we also have to look at things like motivation, not just learning achievement. But is their motivation the same? And when you're using digital content, is there familiarity with ICT content and digital content similar? Because the lack of familiarity is a confounding factor. So equivalence is established on many of these parameters. The previous result is supported and there are some other results here. So what this is, it's a very busy slide. Let me explain this. So it's called interactive engagement versus traditional methods, a 6,000 student survey. Because the data set is very large, it's only across the US, but it's all high school, college students, right from Harvard to the small interior community colleges and so on. People were taught a semester of physics, and there's a standardized, in physics education research, there are several standardized tests, and this one's called force concept inventory. What's meant by standardized test is that these questions, they are multiple choice tests, highly conceptual, so that those are the kind of questions we'll discuss today. And people develop it, in fact, each of these tests is one student's PhD thesis. It takes about 3 years or so to develop and test it for robustness and so on. So when it's developed, when it's declared to be robust, it's a very, very precise test. It can be used across cultures, across different ages and so on. So FCI was one of the first tests of this nature to be developed, and in physics now there are about 15 for each topic. Electrical engineering has one in signals and systems. CS is starting to develop one, I think, and so on. Okay, so after a semester of physics, this test was given before instruction, and it was given after the full semester of physics. Very similar topics. There were about 60 odd courses. And what was measured is it's a standard statistical measure called the normalized gain, and you take the difference of the post and the pre-test, that's called the absolute gain. But the absolute gain actually depends on what the pre-score was. This is for class averages. So students who start higher may not have that much of an absolute gain because they're at a higher level. So you normalize it by the maximum possible score gain that they could have had. So it's 100 or 1 if you're looking at fractions minus the pre-score. And this G factor is between 0 and 1. They looked at, and this is done not for individual students but for class averages. The reds, which are class average gains between 10% and at most 30%, are for traditional lectures. So each instructor was asked to describe how she or he delivered, what happened in the class. So these people said, I gave a lecture. Many of these were best instructors and had very high teaching scores. The greens, which go from about 22% all the way to 70% or so, are the classes where some sort of active learning activities happened. So 2 takeaways here. One is that on average, the gain from active learning courses seems to be 2 to 3 times more than traditional courses. So traditional courses, however good the instructor was, capped at 0.3. Secondly, in active learning, there's a wide range. So what you do and how you do actually makes a difference. Peer instruction, which we'll be talking today, this was another study, it came up out in 2002.
So what is comforting is, however bad the active learning is,
it's at least as good as the traditional. Exactly.
Yeah, which is very good.
Yeah. What is not reported here is what percentage of classes were active learning, how they did it, what they did. This happened in 98, so there's a lot of work done after that. This is from the mid 2000s, where they surveyed about 30 courses doing pure instruction the way it's supposed to be done. 27 out of the 30, 13, the average was 0.4 for those 30 courses. Why Harvard is important here is for 2 reasons. One is that it's Harvard students, and secondly, Eric Mazur, who developed and pioneered this instruction, is from Harvard. So Harvard was not considered in this average. The Harvard average over 10 years, 0.66 or so. Okay, so this is some data. So let's actually move into some specifics. So we know.
So what kind of courses are these?
These are all first year physics courses, mechanics courses, this particular data set. But similar things, not as much, but similar ones have been reported for other courses. So okay, this convinces us to some extent that okay, active learning is good. The next question to ask is how do we achieve it? And as we saw earlier, there are several techniques. In fact, here's a listing of some. The first one up there was our first workshop, which some of you attended. Sridhar Iyer here gave the workshop. It was on a technique called Think, Pair, Share. And today we'll be doing peer instruction. So there are many other techniques. Each one some of them are, most of them are collaborative. But some of them work in both large and small classes. Some are for small classes only. Some take 5 minutes of time. Some are supposed to be done for the entire class and so on. Okay, peer instruction. What is it? It's a question-driven method of learning. Brief one sentence. It's an active learning technique, learner-centric technique. So how is it different from other types of questioning which we happen to do? And we've often heard this word clickers or personal response systems. The ones that we see in Kaun Banega Crorepati that go hand in hand with it. So how is it related to clickers? So let's just explore these questions now. So we'll get started off using an example. And since there are so many people from electrical engineering, this is a 12th standard example. This is a circuit. The yellow circles are bulbs, identical bulbs. You've been told. The battery is at the left and there's a switch in the middle which is open. Everything is ideal. Okay, like you see in our 11th standard textbooks. This is the before condition. In the after condition, the switch is closed. No other difference. Steady state happens for whatever it's worth. The question is, what happens to the brightness of bulb A, the one at the top, after the switch is closed? Does it go up, go down, stays the same, or I don't know. So, take about a minute. Okay, so what you have to do is the following. Right now, don't talk to anybody. Whatever your choice is, hold it up here. 1, 2, 3, 4. I'd like to see all of you, but right now, this is a collaborative activity, but after 1 minute. There are two, one rule and one non-rule. The non-rule is, if your answer is wrong, it doesn't matter. You won't be penalized no matter what. The rule is you have to vote. If you abstain, that's not allowed. Okay, so if everybody could please vote. Okay, so what I'd like you to do is, now you can start talking. Discuss with your neighbor, okay? Find somebody who has a different answer than you. I'll help you find somebody.
If the Prof has a different answer, what should we?
And now the rules are this. Convince your neighbor or be convinced by them. If the two of you have the same answer, turn to the other group behind you. So find somebody. In the end, the goal is to get a class consensus. Okay, so there's somebody who has a different answer. What's your answer? Okay, so you can talk to each other. Yeah. Gargi can talk to Professor Gayatri. Yeah, anywhere. You can form a larger group. It doesn't matter. Just informal groups. If we have 5 electrical engineering profs here, it's like... Okay, so can everybody please vote again, very quickly? Just vote again, or tell me if you changed your answer. That's sufficient. How many of you changed your answer? Let's just see that. 3 or 4 people seem to have changed. Okay, so what is happening here? I'm not going to go into the answers. You have lots of experts among you. I think even though this was a biased sample here, there were about, let's see, about 8 or 9 people who said the answer was 2, 2 or 3 who said it was 3, and 1 or 2 who said it was 1. I mean, my math may be wrong, but 1 or 2, so there were about 5 people who said 1 or 3, others who said it was 2. I didn't make you vote again, but often in the discussion, the answer converges. Okay, one more question, and there's a reason I'm giving you this question. It's okay if you don't try this. This is a little more mathematical. Why I'm showing you this question is, I've taught many times I've taught this electricity and magnetism course, but many times in this particular semester, right after mid-sem, but before I gave the answers, I gave this question. Why is the reason comes here. So this was the original question. Calculate the magnetic field due to a long current carrying wire as a function of distance. It's a very standard. Physicists who teach E&M love this questions like this. 12th standard has a lot of these. What happened is students didn't do very well, and what was expected was an answer where it's a formula. The magnetic field has to be it's a function with distance as the parameter of the function. Students didn't do well. So what I did next is I went and looked why they didn't do very well. And it turns out that question up there, there's an integral that needs to be set up. It's a little ugly, and more than just, it's not just the integral, there is a vector subtraction and it's being integrated over a unit vector. So there's this very ugly r bar minus r bar prime in the denominator, to the that's squared, and on the numerator it's the unit vector in that direction. So it's a very ugly looking mathematical equation. Students always have trouble there. Second problem students had is that the magnetic field, there has to be a vector addition of the little magnetic field pieces that you get from the infinitesimal integrands. And many of them had done something, and the final answers really didn't make sense. They were nonsensical in the sense, we'll see in a moment. If r was supposed to be in the numerator, now it was in the denominator, and vice versa. So what you can do here is, what I did here was I set up a series of pure instruction question addressing. There were two main problems. One is setting up the integral. Secondly, the integral is in the form of dB vector. So the integral is a vector integral. It has to be, there are three integrals you have to do along x prime, y prime, z prime, which is not the good idea, or you do in terms of r theta phi, and it turns out theta and phi integrate out to a constant, and it's only the r unit vector which survives. So that's what really happens. Okay, so what we can do to help students is the following. This is also not written in its full glory, but this was the problematic question, and the earlier question I showed you about the vector subtraction, that was the first question, because students need to realize what it means to do vector subtraction. Then came this question, this is that long infinite wire. Which of these three pink arrows is your denominator? Each one of them underwent a pure discussion, 4 choices, A, B, C, D, discuss with your neighbor, vote if you are different, come to a consensus. So each one took about 5 minutes. Next question was about the direction. So it's okay if you don't focus on the So one question on the unit vectors, one question on the direction of the infinitesimal B field here. So they have to use some right hand rule and realize that it's all in the same direction. So when we give this question, you see the entire class doing all these things. They're discussing with each other. They say, no, it must be into the page, up, down. And by now, once they get these two questions right, they're okay to set up the integral. After this, there wasn't a problem. So that part was just done as a lecture. And finally, this was a question on checking if your answer really makes sense. So, 3 possible equations were given. One has r in the denominator, one is a constant, and one has r in the numerator. And what we asked them is, does it make sense? And they know it's that when this point P goes very far away, you expect the field to go to 0. So which one of these give it to 0? So we want students to be able to conceptually argue and reason. No calculations in any of these. So the point here is we can take a complex analytical problem and break it up into its steps. Many steps are conceptual, requires diagrams, requires reasoning, and then comes the mathematical machinery. Once you get students to that point, they're able to do the machinery on their own. And peer instruction is one way of getting them through these conceptual roadblocks. That, I thought that it's, it looks like it's from the source to the destination. I always thought it was the other way around. Or I didn't realize it was this part of the triangle. I kept thinking everything is from the origin. So students' own difficulties get elicited when they are made to argue through these questions. These are conceptual, but they're challenging. And we're forcing them to think at every step of all the possible choices. So that's another point. How do you write these distractors? We'll come to that in a few minutes. But these distractors have to be very carefully chosen based on what we expect students to say. So what they get at the end is a very physical feel for what happens if this goes up, that goes down, and so on, which is what we want them to do as engineers and scientists. Okay, so peer instruction method, though, especially when you talk to each other. So let's spend a few minutes. What happens as students, or you were students for those 5 minutes? What was it that you were actually doing? Arguing.
Conveying a view.
Conveying your own point of view, trying to articulate and convey your own point of view, okay?
Curious.
Your curiosity, yeah, it got generated. So students are learning some argumentation techniques and all from neighbors around them. Everybody is talking, class is interactive. So there's a host of benefits here for the students. In some problems, in fact, we make them like the representation problems, we make them draw. Students are learning from each other. The points in between are important. So everybody here was paying it, was doing something. I know that all of you here are very special and you do it even if nobody tells you to. But in a regular class also, people who don't know the topic well are willing to think because it's engaging. Their neighbors are doing it. People who know it are also engaged because they're teaching their friends. So it's a good way of addressing intellectual diversity in the class.
You also said that it broke the monotony.
It does break the monotony.
Yeah, they were very happy.
Yeah. To the instructor, it's a huge benefit that the immediate feedback that we get where the class is, it's getting the pulse of the class. The other benefits are to the class atmosphere, that students realize that everybody else is also struggling, and that's a big one. It's unstated often, but everybody, especially in a place like IIT, people feel that, oh, everybody is so smart, I'm the only one who doesn't understand, and this helps them realize that it's not true. And you're building this argumentative but friendly atmosphere, communication, and so on. Okay, so this is just a summary of how it's executed. Right at the top, the instructor asks the question. You may or may not have 2 rounds of voting. The advantages of doing the first round of vote is to get students to commit. In some questions, in fact, single round is enough. But what you absolutely should not omit is this part, the peer discussion, because that's where the learning happens. So you can ask the question, do peer discussion and vote, or you can do individual vote, peer discussion and vote again. It can be done in 2 rounds. What's also very important is this debriefing and class discussion wrap-up that happens later. We didn't do any of it here today. It wasn't needed. But there are some guidelines here on things like getting multiple students to express their choice and reason. Okay, so connection to clickers. The voting can be done with these clickers. What we've seen is that initially many students are very hesitant. But let's say after 4 or 5 iterations, people realize that there is no stakes associated with it. Everybody is in the spirit of talking to each other. So people do let down their inhibitions. A lot depends on how the instructor responds to the wrong choices, because we have to be respectful to the person and the person's reasoning, yet help that person and everybody else understand that there is something faulty in the reasoning. That's good to know, but clickers are not peer instruction really. The heart of peer instruction is in the discussion that's happening in the noise that's happening in the class. So how do you do peer instruction without clickers? There are 2 simple methods. One is with flashcards. You can create these. Those guys up there have it. Second is just take a piece of A4 paper, 4 pieces. I should take a fresh one. And with different colored markers, you can write A, B, C, D. Give one to everybody and they hold it up. very cheap. You can create it in every class. That's one low technology way, or non-computer based technology. Third one is what we saw earlier. The important thing is that in the first round of voting, if you're doing 2 rounds of voting, it's good if students don't see each other's votes because they get carried away by the popular vote. But afterwards, it's okay to tell them that here was the distribution. But it's very important for the instructor to know. That's why I said hold it here and not up here. The clicker helps because the histogram, clicker gives you a histogram of the whole class as well as anonymity if needed, but if you want to track a student who answered which choice, that's also possible. Okay, one slide of research because there's a lot of it. So peer instruction is one of the most widely researched strategies, and why this is a big deal in education research is that very often if one study says that method A is better than method B for some parameter, there is another study done equally soundly which says that no, both of them give the same, there's no difference, and maybe 2 years later third one comes and says no, but under those conditions method B is better. That's a more common scenario in social sciences and in education. PI on the other hand has been shown to be one of the most robust strategies. One of our PhD students did a literature survey in 2010, and she said that at that point, 2010, there were over 300 research articles on PI in various fields. It's roughly in order of how many papers she found. And many are controlled studies it's not just did you like it or did you not like it. I just want to point out two key studies. So this is not one study, several compare courses which is taught using peer instruction with a comparable section. If you have classes sections A and B, A is taught using PI for say 4 weeks and B is taught using traditional lecture, and then a post test is given. So fairly controlled experiments are done, not just with individual students but at the classroom level. And this is few, like maybe 10 or 20 such control experiments are there. This one is a more recent paper and it's very interesting. So what they did here is that they created pairs of isomorphic questions on a variety of topics. I think it was in biology. Students were first asked one of those questions in peer instruction mode, very challenging questions. Then they were asked the second question. You can consider them as very similar questions. In each of the 16, the performance on the second question was much better. It wasn't identical though. Was much better than the performance on the first question. Second question was done individually. They had no training on it. But their conclusion was that the discussion that happened during PI was what helped them understand the topic to be able to answer the second question. And the more difficult the question was, difficult as characterized by the instructor, this effect was stronger. Student perception? Yeah, forgot about this. So there's also a lot of research on students' own perception, and students themselves say, this is all students' own self-perceived. They say that it was because of clickers that I showed up for class. They said that it made them feel part of the class community and made their voice heard and so on. What to do? What should the instructor do? Okay, initially, in the very first question you introduce to a class, you'll see a lot more silence. Yes. So students won't do it, won't talk. But what we've seen, and again this has been reported, is that the more, if you just expect that they will talk, encourage them, crack a joke, give them some incentive, like okay, the first group that starts talking will get a piece of chocolate, do all these things, and they get into the spirit of things. The moment one group starts, the other groups start. So the noise level in the classroom builds up, stays at a plateau for a long time, and when it just starts receding is the time when the teacher intervenes. So I haven't personally experienced a situation where nobody absolutely says anything. One recommendation is that the teacher circulates, goes around, says, let's see what you've done, why don't you think of that. Each activity is recommended to be done between 2 and 5 minutes. And the discussion part especially is about 1.5 to 3 minutes. So the way I know when to stop the discussion is I just listen to the noise. It's a pretty sure way of gauging when people are more or less done. The noise, it peaks and plateaus. It takes some time to build up. That's the hardest time, because that's when you have to be patient and silent. And you let them talk, you let them do, and then it plateaus at a really high volume. Whether it's a group of teachers or small students, IIT students and so on, stays at that plateau for some time, for about a minute and a half, and then starts going down. So when it goes down to, let's say, 1/3 or so from the top, that's a good point to intervene. Again, it's there all towards the end, but since you've brought it up, let me answer. Recommended is about 2 to 4 per class, per 1 or 1.5 hour class. Some do so when I taught EM and PH 103, I did between 1 and 4 per class. And each class was an hour long. People like Eric Mazur do the entire class using peer instruction. He doesn't lecture at all. So students are supposed to read outside of class, come to class, and in the class there is somewhere between 5 and 15 PI questions based on how the discussion goes. So that's in the flipped classroom mode. So what we can do now is maybe spend about 5 minutes or so trying to take one question. If you want to pair up with somebody who's teaching the same course, that might help. And the next part is a little important on what are the different types of questions, how you can construct it, where you should ask it, and so on. So only on page 1 right now. We're still on the first 1A.
So I can pair up, right?
Yeah, pairing would actually. Why I thought this worksheet might be useful is if you want to write a question and use it next week. So, few of you actually seem to have done this the way I had intended it to, because it would be a good idea to just go over it in terms of what their original exam question was, what the difficulty they found, and how they solved it. So I think Professor Gadre was the first one who did it, Udani was the second. So do you want to just go and explain?
This question is very specific to a course called Wavelets. It's an elective in signal processing. But I'll just give a context. So the idea is that what I had done is to ask them about what is, there were 2 spaces and they were asked to find out the orthogonal complement of one space and the other. Basically identify what is more in the second space as compared to the first, what elements are additional. And the catch was that they knew of other spaces where there were many more elements. But here they had to identify specific elements which were more. So I said, restrict yourself to the interval 0 to 3 and which are the additional elements there. That is the crux of the question basically. So how many basis elements does it have which are supported on 0, 3? The difficulty is that, they're not able to identify what the dimensionality of the space, how much bigger it is. I was trying to, helps. This was not a space with which they were familiar in the class. This was a space different from what had been discussed in the class. And their understanding of being able to identify the increment was being tested here. The increment in this space over the earlier space. So
I have a couple of comments here. So a question like this is what is recommended. In the sense, students are having trouble applying something to a new context. I didn't understand any of the technical details of what you said, but I'm still going to say something. But if you only look at the choices where it says 2, 1, 3, 0, we're getting students to think about how many possibilities there are. In fact, the only change I'd recommend here is not to actually give them these specific ones at all. Because that will elicit a lot more discussion. Just say 1, 2, 3 and 0. See what somebody says 2, somebody says 3, and in the discussion it comes out, which are the 3 that you mentioned, the third one is not valid, and so on. So giving a question which takes them, such questions are called scaffolds. So there is a bigger problem they need to solve, but you're scaffolding them, you're giving them a hint through the question that think in terms of how many possible elements there are. Getting them to realize the correct answer for that, and then once they know that it's 2 and only 2, then they can go to solving the full problem. No, but we want them to actually, so the 0, 1, 2, 3, getting them to realize the number and the actual answer they're getting during the discussion. And in such questions, you will say, this is a good question for the 2 rounds of vote, because you will see a lack of convergence initially if they have trouble, and then after discussion, and most likely you will be seeing a convergence here. Since there are so many questions coming up during the discussion on What makes a good peer instruction question? I don't think we have big time to discuss here, but if it is about multiple choice questions, and later we are going to translate to peer instruction questions. But very quickly, if you had to say what makes a good multiple choice question, what are your thoughts? The distractors must not allow for very easy elimination. Okay, I'll just repeat it. Okay, instead of.
Choice should require some thought.
Each choice should require thought to eliminate or to reason through. Okay.
One thing is elimination. That means each choice must probably require some working.
Some working. Okay.
I think that you sort of understand, what's the first way that conceptually this person will think, and sort of anticipate some basic fallacy.
Yeah.
So you add them in, but if there's a way to sort of also hint at that it may not be correct.
Yeah. Actually, the first part of what you said, that try to figure out what are the common errors, common fallacies, and then use those as distractors is the first recommendation on how to come up with distractors. Figure out what your students actually know and what they don't know. There are two ways of doing it. Many ways actually. One is in some subjects these are published. Common misconceptions in signals in convolution. If you just Google it also, it's come to that level. Or ask your colleagues, and if you've taught a course for a couple of years, you know exactly what problem students have. Turn each of the student answers into one distractor. Yeah, but actually, I won't even call it a mistake at this point. This is one way that students think. So in modern education, we don't use the word misconception, we use alternate conceptions. It's a valid way because they have a logical reason to think that. It just so happens that there is something in the logic which needs to be set right. This is the top list is what we want to focus on, that it's usually conceptual, avoids long computations. It should try to elicit students' thinking. That's the point Udayan was trying to make, that try to learn what they know and bring it out. Believable distractors, we talked about it. We'll spend a few minutes on this one now, that questions where students are asked to predict results, what would happen if so-and-so were changed. And then try to show them what actually happens, either through a demo or a video or a simulation. Those are good questions, and effective and good are all in terms of student learning here. All others are good for students' engagement and getting them to interact and the class being lively. All these questions are good for those goals. But if you're looking at student learning, then we want this set. Okay, so I'm going to skip this activity. If you'd like to go back and refine your question later, you can do that based on these recommendations. Let's actually dive into the types of peer instruction questions, because this is what is going to be useful to come up with a question. There are several. I'm going to go through a list of about 8 with examples. And later, if you want, you can stay back after 5 o'clock. I promise Professor Gayatunde I'll finish around 5. So, just, yeah. Oh, I see. Okay. So we can go on. Yeah. Okay. So in the worksheet, it actually gives you some guidelines on how to write questions for each of these goals or strategies, and gives some empty space for you to write. So if you want to stay back and write a few of your own, that's fine. But let's go through the examples first. Okay, so this is type 1. So these are questions where there is a single right answer. It's about some concept or could be a fact. A fact is usually lesser in hierarchy than a concept, but it's important enough. So this is the only example not from E&M and physics, but I kind of like this question. That a small acorn has grown into a huge oak tree. Where does most of the mass come from as the tree grows over the years? When is this question good? Well, when is this question used? If you want to start a discussion on how plants grow, photosynthesis especially, because that's what's creating the mass. So there has to be some conservation of mass. So this is a good question to start off a discussion like that. There is a single right answer, but it's still conceptual. This is what a good peer instruction question does.
Sunlight is massless.
Sunlight is massless. Yeah, that's true. So this is what we use in E&M. There's a parallel plate capacitor, it's charged, battery is removed, some other dielectric slab is inserted. What happens to energy? Again, one of those reasoning things. Does it increase? Does it decrease? So they say that, well, the total charge stays the same, capacitance increases. So all these questions have a single right answer, but they are answered through a set of verbal reasoning, logic, and let me see, it says here. Good questions to write of this type are, does it increase, decrease, does it move to the right or left? Does something, if you're comparing two things, is it more or less?
So 3 choices are okay.
3 is also okay. Yeah. Yes or no is also okay. But yes or no restricts your discussion. Okay, so let's go to another type of question. So the next type of questions, it's still a pure instruction question, but there is no single right answer. You can read this. There is a picture. I didn't. See, this was used to help students how to model a physical system. It's really up to you which ones you consider. There are some important ones, there are less important ones. But questions which can genuinely admit multiple possible answers, like design decisions. Or if you had to choose something, if you have to decide which component to use. Why it's called a discussion question, even though it's peer instruction, is that it gets students, there is no right answer, and students are discussing which is a better answer or which answer leads to what consequences and so on. Okay, so I think we'll have to completely skip it right now. We can come back to writing. At the end, you can choose your favorite goal and write one more. This one is used a lot in physics, that an experiment is described or sometimes shown. And so as you're reading it, I'll try to bring it up. Part of the experiment is either shown or it's described. Students are asked to vote what happens before seeing the outcome. I'd encourage you to go and see this video because it's very counterintuitive. There is a balloon in an enclosed cart, normal cart, it's enclosed on all sides. A person pushes the cart like this. What happens to the balloon? Does it go forward or backward? So this was taught when Newton's laws were taught, and people were, again, there's an issue of modeling, which forces are important, which are not important, and so on. If you use videos and demos in class, use peer instruction questions along with it. They really work beautifully together. Because it gets students to focus on what you want them to pay attention to in the video.
So people end up teaching less.
Content coverage. Actually, somebody asked this question to Professor Mazur also. In terms of quantity, I would say yes.
Maybe less. Effectiveness.
Effectiveness, people have even shown it to be more in the sense that the parts which were not covered, questions on the parts which were not covered were put on the exam after giving it for self-study, and people did fine.
So you can ask them to learn some of the things by themselves.
Either new topics or often what people do is, if let's say there are 3 applications to a concept. One application was done in the class with the full peer instruction and all, and the other application was left out as self-study. Whereas traditionally the teacher might do each of the 3 applications. Okay, other types of question, one more type of question where the reason is embedded in the choices itself. So if you look at something like this, the reason is not there. The students have to say what the reason is during the discussion phase. But here we are asking them to think of the reason when they're making the choice for the question itself. So such questions are good when, such questions, I use questions like this to begin their problem solving process.
So is it possible to give the same option but...
different reasons?
Yeah.
That's what's recommended in fact. So here
it is not done.
Here it's not like that, but in the worksheet if you see it says, maybe give 2 choices and for each choice, give different reasons for the same outcome. For example, something moves slower because it's moving against gravity. This thing is moving slower because there is friction. It's moving slower because there is a drag force. In terms of best practices, these should not be used for quizzes if your goal is conceptual understanding. So don't assign heavy credit. If you do want to assign credit, let it be very tiny for participation only. And without clickers, you can't even do anything. But if you have clickers where you can actually track people, some 2% or 5% of the grade you get for participation, that seemed to help sometimes. That little incentive. But no heavy credit, especially no credit for right or wrong answer. Because the moment there's credit for rightness, the conceptual reasoning disappears. This relates to a slightly different point, but connects to peer instruction, that there's a lot of research on the value of thinking beyond single representation. So making students connecting graphs, diagrams, equations, and interrelating those two. And again, those are a good way of, you can easily construct a pure instruction question with that. Questions, the main question as well as the choices can contain diagrams. I'm going to skip this. This is like if you want to break up a problem, so I'll skip this specifically. So getting, at the end, if you want to recap towards a problem, at the end of a problem, you can ask, so which principles were needed to solve this problem? Okay. You can use very simple questions. This is about definition of a current. If you want to begin a lecture by recapping last week's class, instead of writing a summary, just give a simple, straightforward question. It brings everybody together and you can get started. This has to be done only with a single round of vote. We don't expect wrong answers here. But it's a good alternative to summarizing or recapping last week's class. Okay, so the last step, this is kind of going down in terms of cognitive difficulty. This is useful for a teacher to know. Same method. Several such questions are there. You can ask questions about, if you want to know their opinions about open, debatable problems, energy, climate change, etc., etc. Personal opinions, pace of the class is too fast, all of these. Same method, same execution method. These are not the questions which have been researched about, but it's been mentioned because you can use the same method. Okay, so I think I'll just conclude with this one slide. It's a summary. You can use peer instruction at the beginning of a module. There are certain types of questions. What we'll do is we'll update this worksheet, put all the information. So there's about half a page for each, what type of questions each one is. And we'll post it on our website. So if you want to write one, you can just go and look for guidelines there. You can have questions in the middle of the module. We have seen many of those. And questions to summarize or recap.
This is a very good point to conclude, as she said, and I'm very grateful to all of you for having come today, and we hope that there will be even more people coming in future. You could encourage some of your acquaintances, friends, and people whom you know are interested in the subject to come in future. Thank you so much, and we do hope you'll find these techniques useful in your own work somewhere.
They have a very large set of resources for many things, including clickers. And if you want specific questions before creating your own, you can see what else people have done and borrow and adapt. Because it takes time to develop these. And for these subjects, people have done it and posted it. The thing we need to do is two things. One is we have to create a library of questions. Worldwide, people are working on this. So if you create a question, we'll try to find some way where you can just post it for others to use. What our department is interested in is how does this work in our context, our classroom. We want to have our own pictures. We don't have it today. So if you do it in class, and if you want, what I really want is come and stick a video camera and capture those 5 minutes. May not be the first time you do it, but if it's working in your class and your students are enjoying it, tell us what happened and we'll try to document it. Okay, thank you.